Okay, thank you. Thank you.
Forgetting to talk to you. The first list, would there be any way for me to make that up at a later date? Because I'm that Alex coded or
Yeah, how about this one? You want that one
twice?
twice?
I'll go 100% be fine with that. I know somebody knows my heart. I'm actually really proud of myself.
Okay,
I'm doing
good.
extra problems and stuff.
Good. Okay, we'll just use that twice. How about that? Okay. Yes, times 2. And then take one of those, please. There you go. Take one of those, please. Go probably 3 more minutes. Take one of those, please. Yep. There. Thank you. You need a quiz? You're not going to have a lot of time. Yeah? Okay. Yeah, and then grab one of those. Oh, and you can use your notes. You can use your notes, but still, you've only got 2 minutes. Okay. Here, take one of these. There you go. There you go. There you go. Excellent. Okay, okay. You want to take it to him if you want. You want to take it to, just so he knows what I asked. Okay. Probably about a minute left. Yeah, let's go 1 minute. Okay, and then this is yours. Mm-hmm. Y'all keep it down for a second, please. We got about 25 seconds. that's you. Okay, that's for you. Okay, that's time. Here we go. That's for you. That's for you. Who else? This is for you. Okay. There you go. Oh, shit. Hold on a second. Figure that's for you. All right, anybody else? Hold on, I got something for you here. Hold on. All right, anybody else? Did everybody get a handout? Yes? All right, so how was that? How many of you did the first problem? How many of you did the second problem? Okay. I thought the second one was easier. I thought it was, but.
I can't understand trig.
The trig ones? Okay.
I'm planning to go to office hours and skip class.
Yeah. Okay, well, everyone did something different, it looks like, about half and half. I won't put the answers up right now. We won't work through it. I will say on number one, you had to do integration by parts twice to get it to work. And then the second one, the u sub, the easiest u sub was just u as sine x. And you peel off a cosine, and you rewrite the cosine squared as 1 minus sine squared. And then it's just a polynomial after that. So, all right. We are going to continue what we were doing last class. Remember I said that this section 6.2 is actually two big ideas. And we were working on trig integrals last time. And we're going to finish that up. We have one more example to do. And then we're going to get into trig sub, all right, trigonometric substitution. So this integral is a kind of like a classic integral. I showed you another one last class that I told you was classic as well, that one. But I told you this one, to get that to work, you have to really someone had to figure something out, like multiplying top and bottom by 1. So that one's kind of out of reach for most of us, including me. The first time I ever saw that, I wouldn't have been able to figure that out. This one we should be able to do, all right? And to do this, if we try and just say, okay, well, let's try to rewrite this in terms of cosine first. I could rewrite it as 1 over cosine cubed x dx, right? That's what secant cubed means. But that doesn't really help me because if I try like a basic u sub here, the only choice I have really is cosine. And I don't see the derivative of that anywhere. So basic u sub's not going to work. So let me see what I can do. Really the only other thing I think I have is integration by parts, right? So let me try integration by parts. And what I'll do is I'll go back to the original problem. And I'm going to rewrite it like this. Secant x times secant squared x dx. And the reason I'm doing that is because if I split it up, secant squared, I know is the derivative of tangent, right? So I can try my integration by parts, letting my u be the secant x that's out front, and then letting my dv be the secant squared x dx, because I know the antiderivative of this, right? And then taking the derivative of secant, well, I mean, it's not pretty, but it's something I can do, right? So the derivative of this, derivative of secant x is secant x tangent x dx. That's from Cal 1, right? The derivative of secant. And if you don't have it memorized, you should know that's on your formula sheets. And then this one, I should know, again, from Cal 1, the derivative of tangent is secant squared. So is that all right, everyone? It's okay? Now, I don't know where this is going to go, but I'm going to try it, right? And see what happens. So now this integral becomes, I do the formula ultraviolet. So ultraviolet are these two multiplied, so secant x tangent x, minus the integral Okay, voodoo. I need to multiply that times that. And when I multiply those, what I get is secant x times tangent squared x dx, because I have two tangents that are going to multiply, right, to give me tangent squared. That all good? And I look at that and I'm like, well, that's not any better, right? I mean, like, what am I going to do with this? I can start messing around. Maybe I can rewrite everything in terms of sine and cosine. I mean, there's a lot of different things I can try, but here's where you ultimately are going to need to go with this. And let's just focus our attention on this piece right now. So I'm going to come do that over here. And so what I'm about to show you is just after enough kind of like trying different things, I eventually maybe get to this, where I say, let me try to rewrite tangent squared using the Pythagorean identity. Tangent squared x is what? Secant squared x minus 1. It's secant squared x minus 1. Right? That's what that would be. And that, if I distribute the secant through, is secant cubed x minus secant x, right, dx. And I look at that and I'm like, well, crap. I can do that. I know the antiderivative of that. How do I know? Because we talked about it last class. That was that real tricky one. But it's on our formula sheets. I know the antiderivative of this. I can look at this separate from this because there's subtraction, right? So this is good. That is what? The original problem. And so I go, crap. But hasn't this happened before? Where we had the original problem appear on the other side and then we wound up moving it over and doing some algebra? I'm going to see if that's going to work for me here, all right? So let me come back to this right here. Let me erase this. I'm going to work above this. So I'm back to this. I'm going to rewrite this whole line. This is going to be equal to secant x. Let me do it this way. The original integral that I'm trying to find, right, is equal to this secant x tangent x. The reason why I wrote the original integral is because I'm going to start working with this like an equation. I'm going to move things around. So this is this minus, okay, what does that become? That integral over there, right? Integral secant cubed x minus secant x dx. Y'all following me? Any questions? Am I recording? I'm not muted? Okay. Okay, now the original integral is equal to secant x tangent x minus the integral secant cubed x dx plus the integral secant x dx. So I'm just splitting this up into two integrals and I'm distributing the negative sign through to both. I'm doing that so that I can do what now? Move that one over, right? I can take this integral right here. I can add that integral to both sides. It goes away here. How many of those integrals do I have on the left side now? I have two of them, right? So I have two of the integrals I'm looking for is equal to what was left over here. Still have this, right? Still have this, and I still have to do that, right? So I have secant x tangent x plus or minus? Plus, right? Plus this. Now, we did that last class, right? And it's on your formula sheet. What is the antiderivative of this? Natural log of secant x plus tangent x, right? So this is going to be natural log of secant x plus tangent x. And it should be absolute value. And then I'm going to go ahead and say plus c because we did an antiderivative, right? Any questions? I see looks of like, yes, I get this, and I see some looks of like, what language is this? Right? You all right? What's wrong? Pardon? Oh. Am I done? One more thing, right? I need to get rid of that too. So I just multiply everything by a half. So my final answer is the integral secant cubed x dx. Divide that by 2, so 1/2, and put just 1/2 in front, secant x tangent x. And then plus, and then put a half in front of that. Natural log absolute value secant x plus tangent x plus c. There it is. This is the antiderivative right here. If I take the derivative of this, I should get secant cubed x. That's the last example for trig integrals, right? So I did send out an email yesterday. Did y'all get that? There's that sheet right there that I sent. And what that sheet you're allowed to have on your exams, you're welcome. And it basically summarizes the things that we talked about last class about, what happens if you see, sines and cosines and, the cosine is odd. What do you do? The power on the cosine is odd. What do you do if the power on the sine is odd? What do you do if you see even powers, right? It even gives you the formulas to use, all right? So that way, yes, I do want you to learn it, but, during the test, you'll have something to fall back on, all right? All right, now we're going to move on. And we're going to move into a new topic within this section. And for those of you who have seen trigonometric substitution before, I think you can attest to the idea that this is going to be kind of tedious. All right, these are not the most enjoyable problems out there. So I first need to explain what trigonometric substitution is, right? Because obviously it implies that we're going to do a substitution, right? There's going to be some sort of substitution. Now, we've done substitution in this class already, right? Let me remind you of what use substitution was, right? Use substitution was something like this. Integral, let's just go with like 2x here. Let's go with e to the x squared dx. I almost gave you a problem similar to that today on your quiz, and then I realized, wait, the quiz is not over u sub, it's over something else. So I started over. That right there is a basic u sub. Because we look at it, we see something, right? And we see its derivative. We see the x squared is our u. The derivative of that is 2x dx, right? And so everything matches up perfectly, right? 2x dx, that's this. And then the u up here, right? This u is that. So that integral can be rewritten how? E to the u du. And the antiderivative e to the u is itself plus c, and then you replace u with x squared. That's the answer, right? That's basic u sub. You're looking for something and its derivative. We're going to do something called trigonometric substitution now, and it's not this, okay? So don't confuse it. And the substitution we're going to make is going to be extremely weird, all right? It's going to be extremely weird. So let's start out. I think the best way to do this is to start with an example, just give you the problem and then tell you what the substitution is going to be. Then after we do it, I'll give you the actual note that says what we do in what case, right? If we see this, this is what we do. If we see this, we do something else. So here's the example. First example of trig sub. 1 over the square root of 1 minus x squared dx. Does anybody recognize that that is the derivative of something that you should know already? Inverse sine. This is the derivative of arc sine. We actually showed this when we were at the beginning of this class. We studied inverse trig functions in the very beginning, and we took derivatives of them, and that was the derivative of inverse sine. So the answer to this should be inverse sine of x. But let's act like we don't know that, all right? Let's act like we don't know that. And I'm gonna start identifying the things that are gonna make me start thinking trig sub. So when do I start thinking trig sub? When I see a square root, see here I see a square root, I see a number, see that number right there? I realize that that number is actually a number squared. Yes, 1 is 1 squared, right? Okay, so that is a number squared, then minus my variable squared. If I see this, this is what I'm looking for. Those are my eyes. I'm looking, see? I'm looking for that. I'm having fun with faces this semester. There we go. All right, thank you. So I am looking, right? I am looking to see in my integral, do I see something like that? Anywhere in the integral. Anywhere, right? And I see it, yes? Okay, when I see this, when I see that, here's the substitution I'm going to make. And it's going to be different than this. It's right. I'm not looking for something and I'm going to replace that x squared with u. I'm going to actually replace the x. So in this method, let me do it in red. The trig sub I'm going to do is that everywhere I see x, I will replace it with a times sine of theta. I am making a substitution. I'm replacing the x in my expression with a trig expression, right? Which seems weird because I'm replacing something pretty simple, right? X is pretty simple, right? X. And I'm replacing with something more complicated. A sine theta is more complicated than x is. But this trigonometric substitution is going to get us somewhere, all right? So let's go back to this. What in this problem, what is my a here? What? A is 1. Okay, so I see this. I'm like, okay, great. When I see that, I'm going to replace x with a sine theta. So here comes the substitution. Let x be a times sine of theta. Theta is a variable, right? That is my that is the trigonometric substitution I'm going to make, which is really just x is sine theta, right? That's what it is. Now you might ask yourself, why would you do that, right? Why in the world would you do that? Here's why. Here's why I'm going to do this. Because that square root thing, that square root expression, let's talk about what that square root expression turns out to be. So if I make that substitution, then that square root of 1 minus x squared really turns into square root of 1 minus, okay, what was x? Sine theta, so that's sine theta, right? Squared, right? But that turns out to be square root of 1 minus, can I just say that's sine squared theta? Right? But what's 1 minus sine squared theta? Cosine squared theta by the Pythagorean identity. So this is the square root of cosine squared theta by the Pythagorean identity. And the square root of something squared, these should kill each other off, and we should just get cosine theta. Do you see that? So I have this very complicated square root expression that if I make that trigonometric substitution, it will turn out to be a nice little trig expression, right? And that means my new integral is going to have trig stuff in it, right? And we just spent the first half of this section studying how to deal with integrals with trig stuff in it. So we are taking, the whole idea of the second part of this section is to take things like this and turn them into trig stuff and then use what we've already learned, all right? Okay, so let's back up. I saw this, I was like, okay, when I see that, I'm going to do that. Here, I did it, and then I said, okay, if I do that, then that root turns out to be that, right? So I will be able to replace that root right there. This root that I see right here, right there, is going to be replaced with what? Cosine theta, right? Now, the only other thing I need to do is deal with the dx, because we have two different variables now, right? Like this would be cosine theta, but this would be dx. So I need to handle that. How do I figure out what dx is? Well, I come back over here, right? If this is x, I can just take the derivative on both sides. I can just differentiate both sides of this equation right here. So let me do that. So I'm going to say then, this is this, and since x equals what? Sine theta. I know that dx d theta equals cosine theta. What did I do here? I took the derivative on both sides of the equation implicitly with respect to theta. So what's the derivative of x with respect to theta? Dx d theta. What's the derivative of sine of theta with respect to theta? Cosine theta. Now I will do one more thing. What do you think I'm going to do? Because I'm trying to see what's going to happen to this dx, right? I'm going to move the d theta to the other side. So I'm going to go dx then is cosine theta d theta. Y'all good? So now dx, right? dx right here. That's going to be replaced with cosine theta d theta, right? That right there is going to replace that, and then the blue part, right, is going to be replaced with cosine theta. So I've completely transformed my integral into a brand new integral, right? Y'all ready to write it down? See what our new integral looks like? Any questions? Okay, here's the new integral. Yeah. So my integral is now 1 over what? Cosine theta, right? That's the blue part, right? Right there. Times dx. What was dx? Cosine theta d theta, right? Very important that d theta is there. And do you see what happens to the cosines? They're gone. So this becomes just 1 d theta, isn't it? 1 d theta. Those cancel out. You get 1 d theta. What is the antiderivative of 1 with respect to theta? Just theta, right? This is just theta plus a constant. Okay, we're almost there. We have one more thing to do. Our answer is in terms of what variable? Theta. Our original integral is in terms of what variable? X. We've got to get back to x, right? We've got to get back to x. So to get back to x, what I'm going to do is something we did on the first or second day in this class that I told you we would need later, and that is I'm going to draw a reference triangle. Do you remember me talking about reference triangle in here? Said it would come up again? Today's the day. So now what I'm going to do is I'm going to, let me see, I have some space over here. What I'm going to do is I need to get everything back to x. I'm going to do a reference triangle. And the reference triangle is going to be based upon the substitution that I made, right? The substitution I made was right here. Everyone see that substitution? That was my trig sub. My reference triangle is going to be based upon that equation right there. So let me write that equation down over here. X is equal to sine theta, right? If x is equal to sine theta, then can you tell me what theta is? How could you get theta by itself? You can't divide because that's not like a number. You have to take the inverse on both sides, don't you? The inverse. So if I take the inverse on this side, and then when I take the inverse sine of theta, that just gives me the theta, right, on the right? And then this is sine inverse x, right? Now wait a minute, I didn't draw a triangle yet, did I? I haven't drawn a triangle, but I'm going to draw a triangle, okay, because most of the problems you do, you're going to need to draw a triangle, but right now I could actually say I'm done. Because all we need, our answer was what? What's theta, right? And don't I have theta in terms of x now? So if I replace that theta with sine inverse x, then that means my answer is sine inverse x, what we said it should be, right? But I still want you to see the triangle. We didn't need it for this problem. We'll need it for future ones. How do you draw the triangle? This is how you get theta by itself. But here's how you draw the triangle. You remember that this means that's a fraction. X is x over 1, and I draw a right triangle. This is my angle theta. Sine, by definition, is which side over which side? Opposite over hypotenuse, so that means this side would be x and this would be 1, right? X over 1, opposite over hypotenuse, opposite over hypotenuse. That picture represents that equation, right? That picture represents that equation. And the great thing about this picture is that once I have this picture, I can always solve for this side, right? I'm just going to put it here because we did talk about that before. That would be 1 minus x squared right there. If you solve for that side, square root of 1 minus x squared. And now, once I have the triangle drawn, I can answer anything about theta. If you want to know what sine of theta is, I say x over 1. If you want to know what cosine of theta is, I do this over this. You want to know what tangent of theta is, it's that over that, right? I can get any trig function in terms of theta, right? Any trig function of theta in terms of x based upon this triangle. Okay, that's it. All right? If we see this anywhere in our integral, we're going to do this. So let's do another one of these. All right? And I handed you a sheet here, right? This handout. Let's see if there's one on here that looks like that. Do y'all see any that look like that? Number 1 looks like that, right? Hey, does number 2 look like that? No. Careful. What's the difference with number 2? The order's different, isn't it? Isn't it the reverse of this? Look, so when you reverse this, right, and you put x squared minus a squared is not the same as a squared minus x squared. And even though they're just off by a sign, you cannot pull a negative out of a root. Do y'all know that you cannot pull a negative out of a root? You cannot factor a negative out, because to pull it out, it becomes an imaginary number. So the square root of a squared minus x squared is not the same as the square root of x squared minus a squared. We will deal with that in a moment, all right? We're going to have another case where we do a different trig sub, and there's going to be a total of 3 different scenarios we can run into. But let's focus on this one first. So y'all agree number 1 would be an example? Mm-hmm. What else? How about number 4? Yes. Yeah, 4? 5? No? No, there's a plus between there, right? 7 would work. 15 would work. So y'all pick one. Which one do you want?
1.
You want to do number 1? Let's do number 1. Okay, so integral square root 1 minus x squared over x squared dx. And now look, I told you this, I've been warning you about this from the very beginning of this class. We're starting to get to a place where we have quite a few things we can try, right? We've got like, do we recognize this from Cal 1? We have, does basic U substitution work, right? We have, okay,